Good morning, Fernando. Today we are going to discuss finite state automata with output. Actually, when we are talking about finite state automata, it's a language acceptor. Language acceptor. And here, in this case, finite state automata is producing some output. Producing some output, and there are two kinds of finite state automata with output. One is the Moore machine and the other is the Mealy machine. That means in Moore machine, output is associated with states. That means states are producing the output, and Mealy machine, the edges are producing the outputs. That means here in this case, see, uh, this is an example of a finite state automata with output. This is actually a Mealy machine, and here, suppose that we have the truth table like this. We have, that means binary addition. Binary addition. That means suppose that you have two operands A and B, and the carry is say C, ABC. This is the carry, and what will be the output? This is the output, and this is the carry generated. Carry. Okay. That means 0 0 0 1 1 0 1 1. That means if 0 0, if 0 and 0 is there, then suppose that the carry is 1. What will be the output? 0 plus 0 plus 1. 1 is the output and carry is 0. Suppose that 0 and 1 are taken, then suppose that the carry is 0. Then what is 0 plus 1? 1, 1 plus 1 0. The output is 0 and the carry is also here. The output is 1 and carry is 0. Suppose that here 1 is a carry, 1 plus 0 is 1, 1 plus 1 0 and carry 1. And likewise, you know what is Boolean addition or how binary numbers can be added. Here, like that, here we are going to have same. Say this state Q0 represents carry 0 and the state Q1 represents carry of 1. That means Q0 represents carry of 0 and Q1 represents carry of 1. Okay. That means in this state, suppose that the current carry is 0. That means the finite control is in this state means current carry is 0. And if the input is 0 and 0, if the input is 0 and 0, then 0 and 0, 0 and 0, this is A, this is B and this is the carry. That means 0, 0 and the carry is 0, carry is also 0. What will be the output? Output is 0, and again it is switching to the same state means carry is also 0. That means this is producing an output of 0. That means upon receiving an input 0 0, that means if A and B are, that means the two operands for addition are 0 and 0, then when you are summing up these two plus carry, what will happen? The output is 0 and again the carry is 0. That is it is coming back to Q0. And what about 0 1? That means one of the operand is 0 and the other operand is 1. 0 plus 1 is 1 and 1 plus the current carry is 0. 1 plus 1 plus 0 is 1. That means the output produced is, that means upon receiving two operands 0 and 1, upon receiving the two operands 0 and 1, it is producing an output of 1 and it is coming back to Q0 itself. Why? The carry generated is 0. Likewise 1 0. See, the current carry is 0, and if the inputs are 1 and 0, then 0 plus 1 plus 0, which is 1, and the output produced is 1, and again the carry is 0. That is why these three. That means the four combinations are there: 0 0, 0 1, 1 0, and 1 1. These are the four different combinations of the operands. That means 0 0, 0 1, 1 0, and 1 1. On 1 1, what will happen? As you know, 1 plus 1 is 0 and carry is 1. That means if the input is 1 and 1, what will happen? It is producing an output of 0. That means when we are summing up 1 and 1, the result is 0 and the carry generated is 1. That means the current, it is the finite control is now having the state Q1. Once this 1 and 1, that means if you have two operands, say 1 0 1 1 0 1 and 1 0 0 0 1 0, and suppose that we are going to add these two. Initially, the finite control is in state Q0. And what are the operands? Starting from here, what are the two operands? 1 0. Initially, this will be in state Q0, and upon receiving 1 0, what will happen? 1 0. Upon receiving 1 0, 1 and 0, it is generating an output of 1. This is the output of 1, and it is coming back to that state Q0 itself. That means next state is Q0. It is producing an output of 1, and it has returned to the state Q0. Okay. Now next input is, what is the next input? 0 1. Again Q0 is the state. Q0 is the finite control is in state Q0, and upon receiving 0 and 1 will happen. Upon receiving 0 1, again an output of 1 is produced. Again it is switching back to the same state Q0. What is the next input? 1 and 0. 1 and 0. Suppose that I'm going to rewrite this as 1. This is 1 0. 1 0. Now this is in state Q0, and the next input is 1 0. What will happen? 1 0. What will happen? It is producing an output of 1, and it is coming back to Q0. That means again the output is 1, and it is coming back to state Q0. And next input is 1 and 1. 1 1. What will happen? 1 1 1. 1 1. That means current state is Q0, and if the input is 1 1, what will happen? It will switch to the state Q1, producing an output of 0. That means the output produced is 0, and it is switching to the state Q1. And now the next input is 0 0. What will happen? The current finite control is pointing to state Q1, and upon receiving 0 0, what will happen? An output of 1 is produced, and it is switching back to state Q0. And here what will happen? 1 and 1. In state Q0, we are receiving 1 1. What will happen? Again it is producing an output of 0, and it is switching to state Q1, and that is rest. That means when you are adding this, you have to take. That means here Q0 producing without any input. That means if you are adding this, you get this result. Okay. Now anyway, our point of discussion is regarding finite automata which is producing an output. Here, after receiving each input, that means here for the state Q0 and for the state Q1, the input alphabet, that means input is a pair of binary digits, a pair of bits. Inputs are a pair of bits. For addition, a pair of bits are used, and that means sigma, the input is either 0 0, 0 1, 1 0, or 1 1, and the output produced is either 0 or 1. That is why we have delta is equal to 0, comma 1. That means here the output is producing an output, and the output is 0 and 1. Output is 0 and 1. Okay. And next is regarding, so the formal definition of this is M is equal to Q sigma delta lambda Q0. Okay, that means this is having how many tuples? 6 tuples, and Q is the set of states. As you know, here Q0 and Q1. That means Q is the set of states, and sigma is input alphabet. That means here the input alphabet contains 0, 0, 0, 1, 1, 0 and 1, 1. These are the input alphabet. Then this is the output alphabet. That means output is having output alphabet. Then delta and lambda we will discuss. Delta is a mapping from Q cross sigma to Q. As you know, that means for Q0, that means this is same as that of finite state automaton. And lambda is a mapping. That means for Moore machine and Mealy machine, this lambda is different. That means here in this case, as this is a Mealy machine, for Mealy machine, or initially you have Moore machine. For Moore machine, lambda is a mapping from Q to this one. That means here every state or each state is producing an output. That means once you know the state, the output is well defined. That means every state is producing an output. But in the case of Mealy machine, this lambda is a mapping from Q cross sigma to delta. Okay, this is the difference between Moore machine and Mealy machine. This is an example of Mealy machine because Q0 upon receiving 1 1 it is producing an output of 0. That means here I can write like this: lambda of Q0 1 1 1 is equal to what? Equal to 0. Lambda of Q0 and 1 1. That means it's a mapping from Q cross sigma. Here sigma is 0 0 0 1 1 0 and 1 1. That means in that case, in the case of Mealy machine, it's a mapping from Q cross sigma to delta. And here lambda of Q0 1 1 is equal to 0 means Q0 upon receiving 1 1 is producing an output of 0 and it is switching to state Q1. That means the switching of states is defined by delta. Okay, and this is the formal definition of our M is equal to Q sigma delta lambda Q0, and here Q is a set of states, sigma is the input alphabet, capital delta is the output alphabet, delta is a mapping from Q cross sigma to Q, and lambda is a mapping from, if it is a Moore machine, it is a mapping from Q to delta, and if it is a Mealy machine, it is a mapping from Q cross sigma to delta. and here you have q0, the start state, and here we don't have any final states. Here we don't have any final states because this is producing an output and it is not a language acceptor. It is not a language acceptor, so it is not producing any. It is not having any final states. That means there are two kinds of uh, finite state automata with output. One is the Moore machine and the other is the Mealy machine. In Moore machine, states are producing the output, whereas Mealy machine, edges are producing the output. This is an example of a Mealy machine. This is an example of a Mealy machine. And Mealy machine, the formal definition of finite automata with output is Q sigma delta. This is capital delta, small delta, lambda, q0, and q is the set of states, sigma is the input alphabet, capital delta is the output alphabet, delta is a mapping from q cross sigma to q, lambda is defined for Moore machine like this and Mealy machine like this, and q0 is the start state. This is an example of a Moore machine. This is the input is sigma is equal to 0, 1. That means the input argument is a binary string, and depending on the binary string you have read, that means it is reading the input, and upon receiving an input, for example, suppose that the input is 100, what will happen? It is reading starting from here, it is reading 1 0. After reading 1, that means initially it will produce an output of 0. That means the output is associated with the states. In the case of Moore machine, outputs are associated with the states, and here in the starting itself it is producing an output of 0. That means suppose that your input is 100 and the finite control is like this. Initially it is in state q0 and the output produced is, we are going to write here, this is the state is q0, this is the input. See, q0 upon reading 1, it is in current state q0 and in the starting point itself it is producing an output of 0. Okay, q0 after reading 1, it is switching to the state q1 and the new state is q1 and it is producing an output of 1. That means it has produced an output of 1. Okay, now after reading the next 0, q1 on reading the next 0, q1 is reading the 0 and it is switching to state q2 and it produces an output of 2, producing an output of 2. And now the finite control is in state q2 and q2 after reading 0, q2 on reading 0 it switches to state q4, is switching to the state q4 producing an output of 4. What does this mean? That means initially nothing is there and nothing is there. In that case it is producing an output of 0 means 0. And after reading the first one it is producing an output of 1. After reading the next 0 it is producing an output of 2. And after reading the next 0 it is producing an output of 4. What is the meaning of this? See, this is a Moore machine which is producing an output of modulo 5. That means your input is, say, input is W. Suppose that your input string is W mod 5. That means when you are dividing this, you have to take this as a binary number. This is a binary number, and you have to treat this as a binary, your input as a binary number, and when that binary number is divided by 5, what is the remainder? That means when you are dividing a number by 5, the remainder can be either 0, 1, 2, 3 or 4. That means nothing other than this won't happen. That means either 0, 1, 2, 3 or 4. That is the remainder. That means never it will have a remainder of 5. That is, see, listen here. Here, when your input is nothing, nothing means it is 0 and the output produced is 0. Then, after reading the first string, that means 1. That means it is the binary number 1. And when that number is divided by 5, what is the remainder? 0 is the result and remainder is 1. When you when you are treating this 1 0 as a number, this is actually 1 into 2 plus 0 into 2 raised to 0. That means this is 2. When 2 is divided by 5, what is the remainder? 2. Then after that, it is switching to 0. Then when you are treating this 1 0 0 as a whole, this is 4. And when that 4 is divided by 5, what is the remainder? 4. Suppose that next is 1. What will happen? After reading the next is Q4. Suppose that Q2 on reading 0, it is switching to Q4, and if the next input is 1, what will happen? Q4 on reading 1. Q4 on reading 1, it is staying in the same state. Q4, and it is again producing an output of 4. 4. Say, what is this number? 1001 is actually it is 9. And when 9 is divided by 5, what is the remainder? 4. That means at each stage, after reading the input up to that point, what is the remainder produced? When you are dividing that number 5, and that is the output of this Moore machine. That means if you have an input string and after processing each bit of the input string, it is producing an output, and at that point in time, you have to calculate the binary value of the number up to which it has read, and that is divided by 5, and the remainder is produced as the remainder is the output it is producing. It is producing the output of the remainder. That means when you are dividing a number by 5, the remainder can be either 0, 1, 2, 3 or 4. Okay. So this is a Moore machine which is producing W mod 5. That means W means it's a binary number and your input is a binary number, and after reading each number it is producing an output, and that is the output which is the mod 5, which is mod 5. That means that number mod 5. Okay. And this is the Moore machine, and here what is the output? Here Q is the set of states. Q is Q0, Q1, Q0, Q1, Q2, Q3, Q4. Sigma is this one. Capital delta is equal to, what is the output? 0, 1, 2, 3, 4. Q sigma delta. Then delta is a transition function. Lambda of Q0 equal to 0. Lambda of Q1 is equal to 1. Lambda of Q2 is equal to 2. Lambda of Q3 is equal to 3. And lambda of Q4 is equal to 4. And what is the start state? Q0. And here we don't have any final states. And this is a Moore machine. That means here every state is producing an output. Every state is producing. Now we are going to discuss Mealy machine. This is the example of a Mealy machine. Here the input is sigma is equal to 0, 1. That means it's again the input is a binary string, and input is a binary string, and this will accept all strings, all binary strings which are ending with either 0, 0 or 1, 1. For example, 0, 0, 0 will be accepted, 1, 1, 1 also will be accepted, but 1, 1, 1, 0, 1 won't be accepted. That means all binary strings which are ending with 0, 0 or 1, 1 will be accepted. That means This is accepting, that means it is producing an output yes or no. For example, if you are doing 0, 0, 0, what will happen? Upon reading the first 0, 0, 0, 0. Initially, that will be in state Q0. Q0 upon reading the first 0, this is the output produced. Q0 upon reading 0, it is switching to state Q1, producing an output of no. That means after reading the first zero, it is generating no. That means it is not a string which is ending with 0, 0 or 1, 1. After reading the next zero, Q1 upon reading 0, what will happen? It is reading 0 and it is producing an output of 1 and it is staying in the same state. Q1 and producing yes till now. That means up to this point, it's a valid string. That means it is a string ending in 0, 0. Okay. Then Q1 is reading the next 0. Again it is reading the next 0. Again it produces an output of y and it is staying in the same state. That means up to this point, again that is a valid string according to our definition. That means this will accept a string and say what about 1, 1, 1, 0, 1, 1. Suppose that your input is your input is 1, 1, 1, 0, 1, 1. See, here initially that will be set Q0 and the output produced is this one. Q0 upon receiving 0, what will happen? Q0 upon receiving 1. Q0 upon receiving 1, what will happen? This is actually, this is no. Q0 upon receiving 1, it is switching to state Q2 and produces an output of no. Next is Q2 on receiving 1. Q2 receiving 1 is producing, staying in the same state. Q2 producing an output of 1. That means up to this point it's a valid string. To this point it's a valid string. Again Q2 is reading 1 and again it produces an output after switching to the same state Q2. That means up to this point it is a valid string 1, 1, 1. It's a string ending with 1, 1. Okay. Now next it is reading 0. That means Q2 upon receiving 0, what will happen? Q2 upon receiving 0, it is producing an output of no. That means no. And it is switching to the state Q1. That means no means this is not a valid string according to our definition. And likewise it is happening, and I think you have followed this. That means in a Mealy machine, this is a Mealy machine, and this Mealy machine is producing output. That means after receiving an input symbol, it is producing an output and it is switching to some other state. That means output is associated with edges. That means here only difference between Moore and Mealy machine is the transition function or lambda is defined as is a mapping from q cross sigma to delta output alphabet. This is the only difference, and now we are going to discuss the equivalence of Moore and Mealy machines. Once you have a Moore machine, you can easily convert that to a Mealy machine, and once you have a Mealy machine, you can easily convert that to a Moore machine. Okay. Today we are going to discuss the equivalence of Moore and Mealy machine. Equivalence of Moore and Mealy machine. Here, this is a Moore machine. This example we have already discussed. This is the Moore machine. See, here this finite state automaton is having output associated with states. Here Q0 is, the output of Q0 is 0, output of Q1 is 1, output of Q2 is 2, output of Q3 is 3, output of Q4 is 4. So if you want to convert this to an equivalent Mealy machine, the Moore machine is represented by Q sigma delta small delta lambda Q0 and Q sigma delta lambda dash and Q0. That means here in both the cases, here this differs only in the case of output. That means here it is lambda, here it is lambda dash. All other remains the same. That means set of states are same, input alphabet is same, output alphabet is same, the transition function is same, q0 is same, only difference is lambda and lambda dash. For example, here lambda dash, for the case of Mealy machine, lambda dash of qa is defined as lambda of delta of qa. That I will show you how this is done. So, if you want to convert, that means once you reaches q0, an output of 0 will be produced. Okay. Then what you can do is, here you have to delete this. That means all inputs which are coming to, that means here only one incoming transition for this. That means here from q2 to q0. That means once it reaches q0, an output of 0 will be produced by q0. And as we already know that if you are going to q0, an output of 0 will be produced, and on the fly itself we are producing that output. That means 1 bar 0. That means this will be no more. Okay. Then you are going to 1. That means here only one incoming transition for q1, and once you start from q0 and reaches q1, an output of 1 will be produced, and once, that means the incoming signal or incoming input which is coming to q1 is this edge, and that is also produced an output of 1. Okay, that means here we don't have any no more. That means once you reaches q1, an output of 1 is produced. Okay, see here for this 2, only one incoming transition. Here you have to designate this as 2, and this will be no more. Okay, here from q3, q1 to q3, this one. Okay, say for this q3 there are two incoming transitions from q4 to q3 and from q1 to q3. You have to designate, you have to produce an output of 3 in both of these cases. Okay, then from q3 to q1 you have another transition labeled 0. There also you have to designate this as 1 because q1 is producing an output of 1. Okay, now if you want to delete this 4, if you are converting this, then here you have to add 4, and here also you have to add 4. Okay, I think now I have completed this. So this is the Mealy machine equivalent to the Moore machine we have discussed earlier. That means in the same figure itself I have made the change, and this is the equivalent Mealy machine. As you know, this is producing the same output as the Moore machine. This is the equivalent Mealy machine equivalent to that Moore machine. Okay, now we are going to discuss how a Mealy machine can be converted to a Moore machine. Conversion of Moore machine to Mealy machine is very easy because all the incoming transition, that means here in the case of Moore machine, an output is associated with each states. Output is associated with each state. Okay. So in the case of Mealy machine, the same picture, that means states are same, transitions are same, everything is same. But one difference, that means instead of output produced by the states, we are going to produce output at the fly itself. That means output are associated with transitions. So if you have an output, say A belongs to some state, then if you want to delete this A, what you have to do is all the incoming, here this is an incoming transition, all the incoming transition which is coming to q0 has to designate with an output which is given by this q0, and in that way we can convert a Moore machine to a Mealy machine. Now we are going to convert this Mealy machine. That means this is a Mealy machine, and this Mealy machine we have already discussed. That is, this is producing or this is accepting or this is producing yes when a string is ending with either 00 or 11, and for all others it is producing an output of no. That means it is producing after reading each symbol, it says whether yes or no, and yes means up to that point it is having 00 or 11 at the end, and no if it is not having 00 or 11 at the end. That is this one. So how this can be converted to an equivalent Moore machine? That means here the outputs are associated with transitions, and now we want outputs associated with states. So for that, here Q, the set of states is Q0, Q1, Q2, and the output alphabet is this one. So here we are going to have, say, for the Moore machine is represented by Q sigma the capital delta lambda Q0. Okay, this is the representation of Moore machine, and the equivalent Mealy machine is, for the Mealy machine, the new set of states are Q cross sigma. For example, here we have three states in Q, and in the output alphabet you have two symbols yes and no. That means 3 into no, you have 6 states that are represented by Q0 no, Q1 no, Q2 no. Now here we have Q0 yes, Q1 yes, and Q2 yes. This is okay. These are all states for the new. That means I am going to convert this Mealy machine to its equivalent Moore machine. Here outputs are associated with the states, and now we are going to have Q is equal to Q0, Q1, Q2, and delta is equal to yes or no. When you are taking the cross product, you have Q0 yes, Q1 yes, Q2 yes, Q0 no, Q1 no, and Q2 no. These are the new states. That means for the Mealy machine, the states are Q cross sigma. That means Q cross sigma is the set of states, and input alphabet sigma is the same, output alphabet is the same. Transition function is given by delta dash, and this is lambda dash, and you have the new start state Q0b. This is the new start state. Okay, now here initially it is producing an output of no. That means Q0 or 0 and 1 it is producing no. So this is the start state, and now we are going to have, from this we are going to generate this, and Q0 upon receiving 0 it will go to Q1. That means producing an output of no. That means Q0 on accepting Q0 on accepting 0 is producing to Q1. It is moving to Q1, producing an output of n. Okay, that means here that means upon reading 0, that means if Q0 0, upon receiving a 0, it is going to Q1 producing an output of no. That is why we have Q1 comma n. Okay, If you are in state q1 and it is producing an output of no, then again if it is uh, again if from q1 to q1, if again it is accepting a 0, again what will happen? It is staying in the same state and producing an output of y. That means q1y. That means here upon reading 0, it will move to q1y. q1y. Okay. Now q0 upon receiving 1, what will happen? q0 upon receiving 1, it will move to q2 and it has to produce an output of no. That means q2 no. q2 no means upon receiving 1, it is moving to q2 producing an output of no. Okay. Now after that, in q2, suppose that it is again a reading 1 or it is accepting 1, what will happen? Yes. That means it will move to q2 yes. That means here if it is producing 1, it is moving to q2y. q2y. Now those are the q0, the states of q0 are over. Now q1 no. Suppose that in q1 no, that means if it is q1 no, then if it is accepting 1, what will happen? In q1, if it is accepting 1, what will happen? It will say no. That means it will move to q2n. That means this is q2n. Okay. Now what will happen if in q2 if 1 is accepted? In q2 yes or no? That means this q2 stands for q2 yes and q2 no. And in q2 yes or q2 no, if it is accepting 1, what will happen? It will move to q2y. That means if it is q2 no, if it is accepting 1, it will move to q2y, and if it is q2y, if it is accepting 1, that is staying in the same state. That is staying in the same state. What about q1? q1 no, it is moving to q0, and if it is q1 no, if it is accepting 0, it is moving to the state q0. It's q1 itself. That means upon reading 0. Okay. That means the what will happen if this is accepting 0, that will move to this state, and if it is accepting 1, it will move to this state. And what about this state accepting 0, it will move to this, and it will move to this 0 and 1. What will happen if a 0 is accepted in state q2? If in q2, if 0 is accepted, it will move to q1n. That means q1n is this one. That means this is 0. q1 0. This is q1n. q2n on accepting 0. This will move to q1n. Okay. Now the transitions for q0y also you have to find out. q0y. q0y means initially that may be in q0y or q0n, and q0, suppose that you are in state q0, and if it is accepting 0, what will happen? In state q0, if it is accepting 0, it will move to q1 producing the output of no. That means upon receiving 0, that will move to q1n. That means q1n. That is accepting 0, it will move to q1n. And if it is producing an output of 1, that means q0, if it is accepting 1, what will happen? It will move to q2n. That means that will move to q2n if it is producing an output of, or if it is accepting 1, that will move to q2n, and the transitions for this state is over. What about the transitions of q1y? q1 q1 if it is accepting 0, what will happen? If it is accepting 0, that is staying in the same state and produce an output of y. That means it is staying in the same state, that is 0. And if it is accepting 1, what will happen? Instead q1, if it is accepting 1, it will move to q2n. That means this is producing q2n. q2n. That means the transitions for this is over. What about the transitions of this? What about the transition of this? It is on 0 it will move to q1n, and on 1 it is moving to q2y. And q2y, if it is accepting 1, it is staying in the same state, and if it is producing, or if it is accepting 0, what will happen? If it is accepting 0, what will happen? This state. If it is accepting 0, q2 on accepting 0, that will move to q1n. q1n means this will 0. Okay. In this way, you can convert a Moore machine to a Mealy machine. Here, see, here from the start state, all states except this can be reachable. So, this is an unwanted, or this is not a relevant state. So, this is the equivalent Mealy machine. So, once you have a Moore machine, you can easily convert that to a Mealy machine, and once you have a Mealy machine, you can easily convert that to a Moore machine. And here in this case, one thing you should remember, this lambda dash of here q sigma delta, capital delta, small delta, lambda q0, and one of the difference is here instead of q, the set of states are q cross sigma. In the case of Mealy machine, sigma remains the same, delta remains the same. Delta cap is defined as delta cap of qb comma a is equal to the pair delta of q comma a lambda of q comma a. See, delta dash of qb comma a, that means suppose that q0n means this is qb means here q0n, that means lambda dash of q0n on 0, what will happen? That means here qb comma a means here q0n, this b stands for n, and the input symbol is a. What will happen? That will move to lambda of delta of q comma a. Q comma a means here q is q0 comma a. The input is 0, and here the second is lambda of q comma a means q0 1 0. Okay, what is this? Lambda of q0 on 0. q0 on 0, that will move to q1. That means q1 comma. What is lambda of q0 on 0? Lambda of q0 on 0. Lambda of q0 on 0 is lambda is not the lambda of q0 on 0 is producing an output of n. That means that is why q1 n. That means this in this way it is defined. Okay. Now lambda dash of QB is equal to B. And these are the two results, and this is the way we can convert a Mealy machine to its equivalent Moore machine. So in this lecture we have discussed a finite state automata with output, and the output is associated with states or associated with um, transitions, and the if the outputs are associated with states, we call it as a Moore machine, otherwise it is called Mealy machine. And after that we have proved that if you have a Moore machine, you can easily convert that to a Mealy machine, and if you have a Mealy machine, you can easily convert that to a Moore